Hi everyone. Today we're delighted to be joined by Dr. Katy Clough, who is a lecturer and Ernest Rutherford Fellow at Queen Mary University of London. She's going to talk to us today about numerical simulations of spacetime and the role of high-performance computing. So without further ado, feel free to get started.
Thank you. Okay, yeah, just give me a shout if there are any questions as I'm going through, or yeah, if you can't see or hear properly. So just to check, can you see my mouse on the screen if I wave it around? So
yeah, you can.
Great. Okay. Yeah. So I was asked to tell you broadly about what I do, what I'm interested in, and I'm particularly going to focus on why we need high performance computing to be able to solve the scientific questions that we're interested in. So we use extensively for our work the Dirac facility in the UK. Yeah, we're sort of one of the big users of Dirac, just because the nature of our problem makes it necessary to use high performance computing. So the basic plan for the talk. So I say always strong gravity simulations, and then I'm very aware that often people don't really have a picture of what strong gravity simulations means, and what are we actually simulating? What's the actual physical variables that we need to put into the computer? And I think actually once you understand that, it gives you a better understanding of why you need high performance computing to be able to solve these kind of problems. So I'll start with that, and as I was just saying briefly now, I'm going to try and teach you general relativity in 2 minutes, which is probably a bit ambitious, but let's see how we go. And then I'll spend a bit of time just talking about the science, because I think now is a really exciting time for gravitational wave science. So the things that we can do with our simulations, the kind of questions that we can have input into, are just really broad. So black holes are the things that I'll be mainly talking about. Black holes are the sort of main thing you think about when you think about strong gravity. But there are also questions that I'm particularly interested in about the early universe, so cosmological questions in strong gravity. And then I want to talk finally, so once I've told you about the science, then it'll probably be kind of obvious, what the future challenges are. So I'll just kind of summarize the issues that have sort of come up in the science in terms of the challenges that we need to face, and really why it's pointing us to needing bigger resources in the future. So exoscale is going to be hopefully a big thing for this field and enable us to do a great deal more science. Okay, so what are strong gravity simulations? Well, I decided that the best thing was to say first, what are weak gravity simulations? So here's a weak gravity simulation that I think I stole just from Wikipedia. And this is just the sort of two-body problem in Newtonian physics, where you model gravity as a force between the two objects. And so, the force acts in the line that joins the two objects, and its magnitude varies depending on the distance between them and the relative masses of the objects. And so this is hopefully relatively familiar to people, but this is actually an approximation to the best theory of gravity that we have, which is general relativity. And it works pretty well in most cases, but even Newton recognized that it breaks down at some point, because he had this point that he said, well, what if one of these objects just kind of ceases to exist? The other object will immediately fly off into space in a straight line away from where it was, because the force will just be immediately removed. And he could see that this was kind of inconsistent with the idea that information needs to travel between the object that's disappeared and the object that's going to fly off, in order for it to be kind of consistent with what we think about causality in the universe. So general relativity tries to address that. So first, when does this Newtonian picture break down? So there are 3 real conditions that have to be satisfied. So firstly, well, I suppose it doesn't break down in a non-dynamical spacetime. So I guess what I'm really getting at here is, when do we need these kind of strong gravity simulations? So in general, when we have objects that are just stationary, just sitting there and not doing anything very interesting, then we don't actually need this sort of framework of general relativity to talk about them. We can make kind of approximations. We also, so mainly the case where we need this is where we have very high densities. So we say the gravitational back reaction is high. That just means that the objects are very dense. So this is something like a neutron star or a black hole. So I mean, if these are just, you know, asteroids or planets, in general, Newtonian gravity is just fine. But we know that even Mercury, which is very close to the sun, we see these general relativistic effects on its motion around the sun. And yeah, so no perturbative. So I guess that sort of more feeds into this question of no perturbative expansion, which is saying that basically the size of these objects is similar to their separation. So they're very close together and they're very dense. And that makes them, you know, that makes gravity strong as opposed to weak. So I think most people have come across kind of general relativity, perhaps in kind of popular science descriptions. And you always see pictures like this, where the idea is that now we're not describing gravity as a force anymore. It's a consequence of the fact that space-time is curved around some massive object. So here, you know, we have the sun is in the center of this stretchy space-time, and it's curving it. And then the motion of Mercury around the sun is determined by the fact that it's moving in this curved space. So it's kind of trying to just go in a straight line, but because it's moving on a curved surface, it's naturally going to kind of roll round and round. Like if you've ever put, I don't know, a penny in one of those sort of donation machines where it just sort of spins round and round and round and then falls down the hole at the bottom. So its motion is determined by this curvature. And of course, this is a bit of a misleading picture because it makes a lot of approximations. So the first one is, you know, this is a 2D surface that we're plotting here, that the object is curving, but actually what's being curved is a 4-dimensional space-time. And that's obviously really difficult to draw because you'd have to be able to really draw kind of in 5 dimensions to be able to embed it in a higher dimension. So we always draw this kind of 2D surface representing a 4-dimensional space-time, but it's a pretty good analogy for what's actually going on. It's quite a nice, I think, mental picture to have, as long as you, as I say, account for the fact that that you have more dimensions than what you're just seeing. So as I said, you know, the kind of canonical example of these strong gravity simulations is a black hole merger. So up until relatively recently, so 2015, these were a kind of a theoretical possibility. You know, the idea was that, you know, black holes in the universe exist. So we had evidence already that black holes existed, but we didn't necessarily know that black holes would merge. Right? We didn't know that they would actually be able to get close enough to each other to be able to coalesce and merge in a reasonable amount of astrophysical time. And so it was only when we kind of turned on a gravitational wave detector that we were actually able to confirm that these events even existed in nature. And so it was very exciting that, you know, when we finally got the sensitivity of the detector high enough to be able to detect gravitational wave signals from these kind of events, there was a positive detection. And in fact, there have been many positive detections since. And these simulations of black holes in strong gravity have played a really important role in understanding the gravitational wave signals that we've seen from these events. So I'm involved in this collaboration called GR-CHOMBO, and we develop this specific code and what's called a numerical relativity code for doing these strong gravity simulations. Our code is actually particularly focused on more fundamental physics questions. So there are other codes that are more focused on astrophysical binaries and understanding astrophysical populations of binaries. But we're quite interested in how we can use these simulations to understand fundamental physics more generally. So, okay, I promised you GR in 2 minutes. So here we go. As I say, I think you can get, as I say, from this, I think it's nice to have an idea of really what you're putting onto the computer. So that's what I want you to take away from this. But as I say, if you come away not feeling that you understand general relativity, I think that's perfectly normal. So we're all quite familiar with the idea of flat space. So in flat space, some distance between 2 points labeled by some coordinates x and y is just dx squared plus dy squared. So it's just Pythagoras. And we could write this first expression if we wanted in this matrix form, where we multiply out dx and dy with this matrix that's just the identity matrix. And so that's flat space, that's how we work out distances. It's a slightly unusual thing to write it in this form. We would normally just write it this way, but here we go. And then we could think about the case where we actually had curved space. So now the distance between 2 points is not just determined by the coordinate distance between them. So coordinates are just kind of labels that we apply to, this point and this point. We can see that the actual distance is going to depend on how much the space is stretched between these 2 points. And so what we end up with is actually some functions of x and y that multiply this dx and dy to give us the distance between the 2 points. And so now if we go into what's called special relativity, if we think about having a space-time, so now space and time are somehow part of the same surface, right? That's sort of part of what's called the same manifold. It's exactly the same principle, except that we pick up this kind of weird minus sign. So the c doesn't really matter. C is just a unit thing. C is the speed of light. So in units in which c is 1, this is just a 1 as well. But the minus sign here is really interesting. So the minus sign tells us that, somehow space and time are different, or that we get kind of different effects when we have intervals in space and time. And in particular, what you can have now, you can see that you can have an interval where this distance is 0, or it can be negative, or it can be positive. So it's not a positive definite quantity as it was for space. And that's what gives space-time its really interesting structure of causality. So actually the sign of this tells us whether events can communicate with each other, whether one is in the future of the other, or whether they are, one is sort of, causally unconnected to the other event. So this minus sign really matters, but this is still a flat space-time. And so again, we can have a more general case where we actually have these, instead of having 1 and 1 here, we can have functions. And in the most general case, we can actually have functions everywhere, right? So we can actually have cross terms between the dx and the dt and the dy and the dz and so on. So the matrix becomes fully populated. And obviously we have 3 spatial dimensions plus 1 time dimension. So, here I'm just showing 1 spatial dimension and 1 time dimension. But, we have all of these components, and this is what we call the space-time metric. This is the kind of object that describes how much space is stretched or squashed in some direction. And so this is what we need. This is what we actually want to model. This is what we want to put on our computer. And this has a value. So actually this, it isn't shown here, but this is actually a symmetric matrix. So the xy is the same as the yx. So you actually have 10 components here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 independent components here that describe your space-time and how it's stretching and squashing. So this is just how we describe how space-time is stretched and squashed, but then how that physically evolves over time. This is what's the content of the Einstein equation, of the main equation of general relativity. And what it tells us is that this kind of stretching and squashing obeys basically a wave equation. So, if you imagine this perturbation that I've put in this plot, if you think what would this do next, it would do something, like this, it would propagate like a wave. And this is exactly gravitational waves, right? This stretching and squashing in the space-time propagates, and it propagates from an event that's very sort of strongly gravitating through space to the Earth, where we can measure it using detectors. So there are some complications. So here I've just put a G, But these wave equations apply to all of those components that I was showing you, all of those 10 components, and they're all coupled to each other. So it's not just one equation for each component. They all have to kind of talk to each other. They all have to know what the other ones are doing to be able to decide how they're going to sort of propagate forward. And also there are quite a lot of nonlinear terms in the equations. So one of the main challenges in this field of numerical relativity was actually to find stable formulations for the equations that could be evolved on computers. And they have a source. So if I put this is what I was showing you before. If you put the sun in the middle of space-time, it will stretch it. And so, any kind of source will give you, will generate potentially some gravitational waves. This is what we say matter tells space-time how to curve. So the simulations are very much like if you know about things like fluid simulations, hydrodynamical simulations. They're time evolution simulations where we put in some initial data at some initial time, and we have to specify some kind of boundary conditions. So sadly, we can't simulate the entire universe. Well, I'll come back to that. But in principle, we don't have enough computer resources to simulate the entire universe. So we have to specify some kind of boundary conditions for the quantities. And then we can go ahead and fill this by integrating the wave equation forward in time using the initial data. And so a kind of trivial example of what you could do is, you can just put a black hole. So a black hole is a certain configuration of these G's of this metric, which we know what it is. You can put this in as the initial data, and you can specify that far away everything goes to flat space because there's nothing else there. And then if you evolve this forward in time, it's actually very boring. You would so it turns out, black holes classically, so everything we do is classical physics. We don't include things like, Hawking radiation or quantum effects in our simulation. So for us, black holes are stable objects and they will just stay there, right? So it should just have a black hole, it should just stay there. So I always say this is a kind of a trivial example, but it turns out that actually this is one of the hardest problems to solve in numerical relativity. And one of the sort of main great people in numerical relativity who worked on this for many years, Deirdre Shoemaker, had a real go at me for saying that this was a trivial example, because she said, I spent 10 years of postdoc trying to get this example to work, and it didn't work. So please don't tell people that this is a trivial example. So now I always sort of caveat by saying, this is a hard thing to actually get working in practice. So just getting your black hole to stay there and be stable in your simulation is actually non-trivial. And mainly that's because black holes have this unusual property of having this singularity at the center of them. So we actually don't know what happens at the center of a black hole. We end up with infinities in our equations. And obviously, computers don't like infinity. So that's kind of problematic for modeling them. And we have to find a way to deal with that infinity that we get at the center. So yeah, so why do we need HPC for this? Well, I've kind of tried to allude to this. If you think about this system that I've described, we've got 10 components. So it turns out we actually need 20. We need these components. We also need their time derivative because it's a second order differential equation. So to solve this, our initial conditions are both the thing and its first derivative. So we have 20 components, and these exist at each point in the physical domain. So we have a three-dimensional domain, X, Y, and Z, and we need to specify at each point what these 20 values are, plus any matter. So if we're doing neutron stars, then we have some kind of fluid that we need to describe at each point. So if you think about that, that's a huge amount of data. So in particular, it's a huge amount of data because we need incredibly high resolution of these black hole objects. So one of the things that always surprises people when they start out doing these simulations is just how high the resolutions are that you need. So I don't know, it's like, I always say to people, it's like making mashed potato, and people tell you if you want really good mashed potato, you need like more butter. And you say, oh, but I already put a lot of butter in, it seems like it should be enough. And they're like, no, more butter, right? Like that's how you make it really good. And it's the same with these simulations. These objects look like they're quite smooth. So you can think of these as being kind of potential wells. So they're actually some measure of the determinant of that matrix that I was showing you, but they correspond in some way to a potential well, you know, that things would fall into. And as I say, naively, they look kind of smooth. To me, this looks like it's over-resolved. It looks like I'm using too many points to describe the horizon here. But actually what you'll find is that if you use lower resolution, then they'll evaporate or they'll start to go away from each other instead of towards each other. It's related to the kind of the causal structure of the space-time. So near the horizon, everything has to go in, and you need to resolve that very well to be able to describe the system. So one of the challenges of these simulations is that you do need really high resolution. And you can see that what's going on here is that we're using adaptive mesh refinement, where we use high resolution in those areas, and then we kind of step down to a lower resolution far away, where we don't need so much information, where there's not so much going on. But we can't sort of step down forever. So we can't just go to a very, very coarse resolution, because what we're actually interested in these simulations is extracting these gravitational waveforms. And so these gravitational waveforms actually need to be extracted kind of far away. So, I mean, this ring that I've drawn is far too close to this binary black hole to be practical. But, you know, imagine it sort of a bit further out. On that sphere that surrounds the black holes, we're going to basically measure these waves as they pass out. And what we measure, usually we measure the kind of spherical projections. So modes like 2-2 mode, 2-1 mode. So in like the same way as a sort of atom state, we measure the spherical harmonic modes of the waves as they propagate away from the binary. And then we can imagine that we have these waves propagating away, and we can then say, okay, imagine I'm sitting here at some distance from the black hole. What do I actually see, right? I have a detector. What's the signal that I measure? So the signal that's measured by the detectors is a strain. So it's a change in length over a length. So I won't go into the detector and how it works, but it's really, really nice. You can sort of Google how these detectors work, but they're really measuring the fact that, as I say, space is being stretched as the gravitational wave goes through it. And so there's a change in some fixed length, there's some change in that length as the wave passes through. And so this change in length is what's being plotted here. This was the first detection of gravitational waves by the LIGO detector. And what's nice is that they put numerical relativity into the plot. So that was really, really nice for me, because it means whenever I show this picture of the first detection, you can see in a way how important numerical relativity is. So it was really used to kind of match the signal that was detected, and then understand its properties. So understand the mass ratio between the black holes, how their separation changes over time, and how their relative velocity changes over time. So this was to tell you, this is why we need high performance computing, because we have, many variables that we're evolving over a large domain. And that domain, we need to resolve scales, sort of large scales that are far away from the object, and also very fine scales that are close to the object. So, if you think about adding up all of that data at different points in the domain, you can see that that's going to be, potentially it can be, terabytes of data for a simulation over many time steps. And all the calculations that involve all of these quantities at every point, we're having to evaluate many updates essentially for these quantities over time. So this is the main sort of challenge that I wanted to tell you about, but I did just want to highlight this other problem in gravitational wave physics, which is then what we do when we get the signals and we have these numerical relativity waveforms. And of course, what we want to do is to be able to map between the signal that we see. We want to see this one signal and say, okay, that corresponds to a black hole pair where, one had this mass, one had this mass. It's so many light years away. The spins of the objects are a certain value. So this is what I'm showing here, this nice triangle plot is only a subset of the possible parameters. So I think there are 15 parameters in total to describe fully a binary black hole event. And this is, this is the masses, the mass ratio, and the effective spins. And, we're trying to infer these from the signal that we have. But if you, I have a slightly sort of cosmology background. So in cosmology, we have very sort of simple models where you can immediately, get your likelihoods for the data given some parameters with a very quick model. But the problem that we have in numerical relativity is it's very hard to create your data from a certain set of parameters. So every possible combination of masses, spins, distances, and so on, I have to run a different simulation. And so, one of these simulations will take a week. So I can't possibly sample, my whole parameter. I can't just, go and grab a sample in sort of, milliseconds or whatever you want to do. It's just impractical. I have to go and run a simulation for each case that takes a week. And so there are these waveform catalogs that are generated where each of these signals has some different combination of parameters like masses and spins. And then what we have to do is build models that kind of interpolate between those values so that this model can be used in place of the real simulation. So the value in the simulation is in a sense validating these more sort of continuous models that are then used in the data inference side of things. But it's a kind of a big, the sort of the inference side of things, the data analysis side of things is highly non-trivial just because generating, as I say, one template, one waveform for one set of parameters is incredibly expensive. So we have to be a bit more clever than we are in perhaps some other areas. Okay. If anyone wants to shout out with questions, they can do that now, or I'll just continue to tell you what we want to do with our numerical relativity simulations scientifically. Okay. So I think, the primary goal that most people talk about is the kind of astrophysics. And this is really exciting. So learning more about the astrophysical black holes, but I think really particularly how they form. So it's incredible really how little we know about black holes. So when this first event came out from this binary black hole merger, it was incredibly surprising because it was the masses of the objects were sort of tens of solar masses for each of the objects. And at that time, most of these kind of stellar formation, supernovae, black hole formation models were predicting black holes that were sort of several solar masses, or 5 solar masses, maybe 6, 7, 8, but not 30 or 40, which is what we saw. So already this first detection kind of turned on its head what we thought we know, or what we thought we knew about sort of stellar formation and black hole formation channels. So, and it's been like that kind of ever since. So then, people went and revised their models and said, okay, no, we can see how we could form these black holes that have these masses. But you definitely can't have any black holes that are between 50 solar masses and 100 solar masses, or something that we call the mass gap, because if you see them in this, then we really don't understand how they form, because there should be these processes that prevent us forming black holes in this range. And then, a couple of years later, there's a black hole observation that's right in this window where people said, well, we shouldn't see any there. And so this raises the question, well, is this then because our model's wrong? Or is it because it's a second generation black hole that's maybe come from an original merger? So 2 objects that were below this threshold merged, and now you have this heavier object that goes on to participate in another merger. But then this already sort of turns things on its head, because to have the time to be able to have not only a first merger, but also a second one, that's again kind of inconsistent with what we think about how black holes exist in the universe and how clustered they are. So as I say, all of these observations of black holes and their signals are really kind of revolutionizing, I think, a lot of what people know about astrophysical black holes. So this is a really exciting field to be working on. And the reason why it's particularly exciting, so this is the graphic after there were a few events. They made this beautiful graphic. So LIGO made this, and each event is kind of detailed in, quite a lot of detail, given of their relative sort of distances. So these positions are not known very well, but, the distances are known relatively well, but they're all, all these facts are given. And then very quickly, they stopped giving too much data on any of the objects because, it starts to get too busy, like the plot becomes too busy. And so these plots show the initial objects and how they merge to make the final object. So this is what I was saying about having the initial, this was the first detection. It was sort of 30 and 40 solar masses. And then, we're actually here now in terms of the data that we've gathered. So now no one really cares about this particular event and its parameters. We're into the field of starting to do, statistics essentially with the data, because we have enough events that we can start to make inferences about the populations from which these events have been drawn. But, this is by no means the end. I mean, actually, I think that this plot is even out of date because this is the 02 data. And I think we've now done 03 and we're in 04. So really, this should be even bigger. And, we're having almost like an event every day now when we turn the detector on, because the sensitivity is just getting higher and higher. So the amount of data that we're going to have in the future is just going to grow kind of exponentially. And, at some point, we're going to have to, do inference on this enormous sort of data sets. And the simulations that we do are going to have to feed into how we interpret all of these signals. So I took this slide from a conference I was at, just because I thought one day in 20 years time, I'm going to go back and look at this photo and be kind of amazed by it, or, it's going to give me some interesting memory. So this is including the next generation detectors, the Einstein telescope, and LISA, which is a space-based detector. And it's showing how the signals we see and will see are related to the redshift of the object. So, local universe is much less than redshift 1. And, here we're looking back to essentially the furthest we can see, right? So the beginning of the universe, as we look further away, we actually see further back in time. And with these future detectors, at the moment with this tiny green region here, and I was showing you all of these events that are happening, we're going to be going all the way back to here. And for me, that's really exciting because we actually have no idea what we'll see here. So at some point we should stop seeing black holes. Black holes should form somewhere. I can't even remember where, maybe Z is 10. And if we start seeing black holes before Z is 10, then we really don't understand the history of the universe that well at all. And they must have come from some other physical processes other than stellar collapse, which is what we kind of expect. So this says in about 20 years time. And, I think there were people in the audience who were sort of sitting there thinking, I hope I'm still alive in 20 years time, that I'm going to actually see this. Slightly harshly, but I really thought, I really hope that in 20 years time, I'm here to see the results of what happens with this, because it's going to be an amazing amount of data, and it's going to tell us so much. And I'm sure there are going to be some surprises in what we see. So yeah, as well as learning about the black holes themselves, we're also really interested in learning about their environments. So this is a picture of a black hole. So this comes from the Event Horizon Telescope. And it's kind of cheating because it's not really a picture of a black hole. It's a picture of an accretion disk around a black hole. But of course, we see that the black hole is there because we have this region where no light is coming out anymore. And that's representing essentially the horizon of the black hole. And we would like to learn more about the environments in which black holes live. So that is primarily the baryonic environments, so things like accretion disks. but also things like dark matter, which we don't understand very well at all. There are scenarios where dark matter clusters around black holes, and then we could find some evidence of what dark matter is from looking at the way it impacts on these gravitational wave merger signals. So this is actually one of the main focuses of our group. I said that we don't do so much astrophysics. We're actually interested a lot in fundamental physics. So one of the questions that we're particularly interested in is whether GR is the right theory, even at these very high energies and densities that we see in black hole mergers. So there's a possibility. This is kind of a regime that we've never probed before. So we've tested general relativity in our solar system. We've tested it on cosmological scales, but we're now seeing signals from very close to, that are really coming out very close to the horizon of some very compact objects with very high curvatures in the space-time. And so it's possible that at those very high scales, you start to see some new physics coming through. So in the same way that Newtonian physics broke down and you had to go to GR, at some point we expect that GR must break down and we'll have to go to something else. And we don't really know what that is, but okay, we expect that there should be some modification. And so if we do have modifications to general relativity, these signals will look different. So here is an example of how that happens. So the blue one is, you can't really see because it's basically on the same, this is it blown up. It's the blue one, and the orange one are very similar because that's a very small modification. But it takes a certain amount of time for the black holes to merge. And if you add these modifications to gravity, then in general, what they do is they speed up the merger. So in general, they give you some other way to lose energy from the system or lose angular momentum from the system. And so the objects will generally in-spiral faster. And so this is something that we could potentially pick up in the signals if they're merging faster than we expect from their other parameters. And of course, the problem is that, that's not how you do inference, right? Like you don't get the other parameters given to you and then you go and check whether this one's different. You have to fit all of the parameters together. So what we want to know is, is there any kind of, is the model, is what the data we're seeing more consistent with a model with these modifications than it is with the standard general relativity model that we use normally. So yeah, so our group is, as I say, particularly focused on how these modifications to gravity change the waveform. And it's actually a big challenge to put these modifications into the code because they really increase the nonlinearity of the simulation. So already GR is a very nonlinear theory, and then we add in these kind of additional modifications to gravity. Okay, so something let me check how I'm doing for time. Yeah, okay. So one of the things I said I was particularly interested in was looking at cosmology and the early universe. So particularly I'm interested in, so the universe on very large scales is very homogeneous. So if you look in this direction or this direction, okay, close to us, things look different because maybe the sun's in that direction, maybe it's not in that direction. But as you go very far away, things start to look very homogeneous on large scales. And we actually don't have a fantastic explanation of why that would be the case. And if you kind of rewind the universe is expanding, you get to this point where you end up with a singularity, where you end up with kind of everything that's in the universe is now, in our visible universe at least, is concentrated on a single point. And our theory kind of breaks down. And so if you do that, actually what you expect is not to get to something very smooth initially. You actually expect to start with something that's very inhomogeneous. And so what we can do with these simulations is kind of explore how that process happens and how, if we add new physics, that changes how we smooth out the universe or don't smooth out the universe. And we can try and understand what the processes are that have led to the universe that we find ourselves in, where things are very homogeneous. So this is something that people don't traditionally think of when they think of these strong gravity simulations. They think of black holes. And you can form black holes in these simulations. Like if you get big overdensity, you'll end up forming a black hole. But here you're really interested in, as I say, sort of doing a kind of numerical experiment on how the universe evolves to try and understand, the features of the one we're in. So I have a very small digression, which I think I do have time for, just because I wanted to say why the universe, in particular the early universe, is a very strong gravity system. And we don't usually think of it as being a strong gravity system. So we think that the universe we live in is kind of flat, but it's actually flat in space and not flat in time. So we can actually, go and do things like measure triangles. So if you imagine having like a giant laser that you fired the laser between you and a satellite over here and a satellite over there and then got it back. If you do that over a very short time period, you can measure the triangle and measure the angles on the triangle and check that they add up to 180 degrees. And that's consistent with the space being flat. And that's broadly what you find. They don't do it that way. That's not how you do it in cosmology, but that's the basic principle. Whereas if space was very curved, like on a sphere, the angles of a triangle add up to more than 180 degrees. And on this other shape, on this kind of Pringle shape, they add up to less than 180 degrees. And so we can measure how curved space is, and we find that it's actually roughly flat. But space-time is definitely not flat in our universe. It's very curved in this time direction. And this is what we usually describe as the expansion of space. We say that, two objects, two galaxies or clusters of galaxies over time are moving apart. But it's actually because the time part of the surface is very curved. And I try to illustrate this always by telling people, well, you don't think, I hope, that we live on a flat Earth. But if you did, if you really thought that the Earth was flat, and you did an experiment where you and your friend started in, different parts of Africa on the equator, and you both say, okay, we're going to head north. I'm going to head north here. You're going to head north here. If you were on a flat Earth, you would just keep us the same distance apart. So you would keep going north, and you would stay, if you're always, fixing your eyes on the horizon, walking in a straight line, sometime later you would still be the same distance apart. But what you find on the Earth, because it's curved, is that actually you would come together, right? If you both head north, you end up joining each other at the North Pole. And so you might naively say in this case, oh, well, some force has maybe pulled us off course. If you wanted to really believe that the Earth was flat, you would postulate some extra force that was pulling you off course. Whereas, you can see that what's happening here is really that you're moving on a curved surface in a straight line on a curved surface. And that's what gravity is, right? We would describe, if we really insist that we think that the universe is flat, we believe that we're just, moving in straight lines. And so, some force must be pushing us together or apart. But in fact, it's related to this idea of curvature. And so, most of us probably think, or maybe we don't think about it at all, but probably most people don't think about it, but, we would naively say we live in a flat universe. And that, if two of us were sort of just floating around in space, some distance apart, sometime later, we would find ourselves the same distance apart. But what we actually find is that we're moving apart over time. And as I say, this is related to us moving on this curved space-time. Rather than some force actually sort of pushing us apart. That's not what's happening. So yeah, so the description of this curvature in the time direction, once we add in large inhomogeneities in space, so once space is not the flat surface that I showed you, once it's got some bumpiness in, which is what we kind of expect at the beginning of the universe, it's actually very hard to predict what's going to happen next. And that's when we need to turn to these simulations as kind of numerical experiments to explore kind of what I say here, sort of possible beginnings to the universe. So we don't really know what happens. We have this kind of picture. We have this phase called inflation that we think explains why the universe is very smooth. But actually how to get inflation started is not incredibly clear. And there are some potential issues with that. And we have alternative models where we actually have a bounce in the universe. So actually we're expanding now, but in the past we were contracting, and then we went through this, what's called a bounce, that's like this bottleneck. And this too is not particularly well understood, how we could obtain such a bounce in our universe, particularly where we have strongly inhomogeneous spacetimes. So yeah, that's my mini digression of when you think of numerical relativity, don't just think of black holes, think also of trying to understand sort of cosmology, particularly in the early universe. Okay, is there anything else? So I think I've covered most of the things that are interesting, but I have one final kind of silly thing, which is a slight hobby of mine, which is trying to simulate warp drives in gravitational waves from warp drives. So it turns out that you can, so this is, I don't know if people are Star Trek fans. If you're not a Star Trek fan, maybe you just want to turn off now. If you are a Star Trek fan, you probably find this exciting. You can actually build the space-time of a warp ship. So the idea is sort of, this is a cartoon in the top half where the space-time in front of the black hole, in front of the ship is kind of collapsing, and the space-time behind it is expanding. And this contraction and expansion kind of drives the ship through the space-time, potentially faster than the speed of light, but definitely, can propel it through space. And you can simulate this. So this is what this is measuring here, is the expansion and the contraction. So red is contraction and blue is expansion. So this is the initial condition for this warp bubble. And what I can do is I'll play this as a movie, and you'll see what happens to the warp bubble. So the problem with the warp bubble is it's unstable. So you have to kind of imagine that aliens have like broken their warp drive, or their warp containment field has broken down or something like this and collapses. And I'll show you what happens. So I think this may have sound effects if things work properly, but we'll see. Okay, so I'll play it again. So what you can see is that it's very bad for the people in the ship if their warp bubble collapses, because these contracting and stretching regions come into the center and then sort of blast out again. So anyone who's in this ship is going to be torn apart basically by tidal forces. So let me play that again. Yeah, so it's very bad for the people in the ship, but you can see that there are these kind of waves going off away from this collapsing warp bubble. And we can actually extract the gravitational wave signal from this, which I think is quite cool. And we could, in principle, go and search for this in the LIGO data. The problem is that the LIGO data is full of glitches from like physical effects that look quite a lot like this signal. So we're a bit reluctant to go and search for it in case we actually find it. And then, then we're in this kind of, we don't really know, should we say we've discovered alien warp drives? Probably not, probably it'd be the end of your career. But anyway, it's mainly just a sort of fun project.
Don't lie.
So in the last couple of minutes, I'll just sort of summarize, what the big challenges are. So basically, we just want to go sort of bigger and faster. So we have some size of our domain. So in the cosmological case, we want our universe to be bigger. We want to be able to resolve greater ranges of scales. If we have a small object going around a big object, this is a big target of LISA. To be able to resolve the small object while also resolving the big object is very challenging, and really pushes our current numerical relativity simulations to the limit of what we can do in these kind of 1 to 100 ratios. And you can't do this with perturbation theory. It's not accurate enough. So you really are going to have to sort of push to this scale with your simulations. The same applies to time. So if we want bigger space, we also want longer times. We only really follow the last few orbits of the binary. We would like to sort of start when the binary is sort of further out, and really, you know, for a lot of these models, we need to match to some perturbative expansion. And maybe, you know, the time scale that we're doing that over is not very clean to do that match. So we would like to start earlier when it's really in this perturbative regime. We want to increase the parameter space we can. So I said that this was a restricted amount of the 15-dimensional parameter space, and people do generally fit a restricted range of parameters just because the simulations that we have, so this catalog of simulations, doesn't include all possibilities by a long way. So particularly things like eccentricity or spin, unusual spin configurations are not very well represented in the catalogs. And obviously that impacts on the models that you can build from them, and therefore on the inference that you can do with those parameters. So we would want to increase the parameter space for which we have these waveform templates from which we can build phenomenological models and use them for inference. Yeah, and then, you know, if we want to describe new physics, actually what this means really is including new parameters into this 15-dimensional parameter space, making it sort of 16 or 17-dimensional. And, you know, from an inference perspective, that's okay. We can cope with, you know, 17-dimensional parameter spaces. But again, it's coming back to this problem that every simulation we do with every set of possible parameters, you know, is taking us a week to do. And so it's really limiting the kind of the physics that we can include. And then this plot, I think, is a bit difficult to read, but I can tell you, you know, just in summary what it means. So this is talking about the network SNR, the signal to noise ratio, from future detectors. So these ones at the top are the future detectors. So this is the Einstein telescope, the one that's going to cover a lot of the universe. And when we get to this, we get very high signal to noise ratios. So we're getting into the point where we're really signal dominated rather than noise dominated. And then the kind of the errors that we find in our data, the errors that we identify, the mismatch in, you know, matching up the templates to the reality, really, you know, goes down in this way, in such a way that at some point you become dominated by the numerical relativity error. So once these lines cross the kind of the green band, essentially our numerical simulations aren't good enough anymore. The errors that we have in our numerical simulation are comparable to the kind of the errors due to the noise and things like that, and therefore we won't be able to distinguish between them. And so we'll have some potentially, you know, we'll infer some errors in the inference of our parameters, you know, that are significant. And so we need to do better with the simulations that we have. Okay, so to do this, we're developing a new code called GR Teclin. We're taking our old code, GR Chombo, and we're upgrading it so that it works in particular with GPUs. And this is quite challenging, but we are getting a lot of help from our RSE friends at Dirac, so Juliana, Mirin, and Casper in particular. Yeah, we're really excited about this. So we think this is really going to increase a lot of what we can do, but it's probably not enough, even just doing this. Like, we need to probably think of really new paradigms for how we do these simulations that will in particular reduce the error and increase the kind of speeds that we can get. So yeah, that's it. In summary, you know, strong gravity simulations, it's a very exciting field, but they are technically challenging and costly to run. So as I say, we are developing new numerical techniques. We are upgrading our code to be able to transition more to exoscale machines, but you know, it's going to be challenging even so. So yeah, thank you.
Great, thanks very much. Really happy to see Juliana then. So Juliana was at Liverpool until last year, working.
Ah, yes, of course she was. Yeah, right, of course. Ah, I didn't even think of that. It was not at all a plug. She's fantastic. Yeah, she's been really helping us out.
Yeah, she's great. I'm glad that she's working on such an interesting project.
Hmm.
So we'll take questions from the room first, and then if anybody's got any questions online, I can see a few hands raised already. We'll go to that. So anybody in the room, any questions? Yeah, Emily.
Hello, thank you for your talk. It was super interesting. So I look at the impact of black holes on our environments, but in like large scale cosmological simulations. So I'm using Flamingo. What is the resolution and box size of your actual simulations? Because they seem to differ so much, and it's super interesting. I never really hear about because I'm so pigeonholed into my large scale simulation.
No, I think we're all a bit pigeonholed into what we do. I mean, that's I think one of the main challenges, and you know, this is what I was alluding to at the end with the scales issue. So I mean, yeah, your cosmological simulations, you know, you're not resolving the scales that we're looking at around black holes, right? You know, for you, that's kind of coarse grained, and you use some subgrid physics model to model how black hole feedback works and things like that. But we're on, you know, much smaller scales. And for us, it would be incredibly challenging to go to those much larger scales and still maintain the resolution that we need around the horizon of the black hole. So for us, what's really difficult is, for us, the boundary conditions of our simulation kind of set a lot of the physics. And we would like to infer those boundary conditions from what you're doing. So we would like you to tell us, okay, at this, you know, at this distance from the black hole, we expect the density of baryons to be this, we expect the dark matter density to be this, but those scales are still like well separated in terms of, you know, in terms of the scales. So I mean, for example, if we're talking about you know, a supermassive black hole, if we model one of these as a supermassive black hole, our box is sort of a parsec of order, which, you know, is well below the kind of scales and resolution that you're using in well, normally in cosmological simulations. So there's this huge divide, I think, between these two fields. And like bridging that gap is really hard because, you know, for us, it's really hard to get bigger, and for you, it's kind of hard to get smaller. So, so I think that's one of the interesting challenges in the future.
Thank you.
Any more questions in the room? Oh, okay, then we'll go online. So Aravinda, I think you put your hand up first. You should be able to unmute yourself and ask a question.
Hi, really enjoyed the talk. Thanks. Going back to the AMR bit, I was really interested to see how, if you don't resolve the horizons, then I think you mentioned that there's kind of macroscopically different behavior on the grid.
Yeah.
So I'm wondering, the intuition I'm getting is sort of that because you can't resolve the singularity, you need to put that information on the grid, so you need to make it denser nearby. Is that sort of accurate?
It's kind of that. So it's actually more the horizon of the black hole. So the singularity is one of the actual sort of nice features of general relativity, is that this singularity is hidden within this event horizon, and everything goes into the event horizon and nothing comes out. So if we have actually numerical noise, which we do around the singularity, because we can't resolve something that's infinite, it's like an infinite spike, we can't resolve it. We get a lot of numerical noise, but it doesn't propagate out into the rest of the space and time because of this event horizon structure. But one of the things that we have to do to be able to prevent that mess from propagating out is we have to really accurately model this horizon so that it really is a kind of purely ingoing boundary surface. So I guess it's like trying to apply a purely ingoing boundary condition on this quite small sphere. So I think that's my intuition of why we need this really high resolution. But in a sense, it's kind of like it's kind of just, we tried it and we find that, you know, if we don't use it above a certain resolution, we just get, as I say, they don't converge, like the simulations don't do the same thing. So it's really sensitive to this, and in a way which, as I say, I think is, you can justify it, but it's still quite surprising how high the resolution is that you need.
So it's more the event horizon that needs to be resolved, not really the inside part of it.
Exactly, yeah. So
Okay.
we actually, we don't resolve the singularity almost at all. So there are people who are interested in doing simulations of what happens within the horizon. But from an observational standpoint, nothing that happens in the horizon should affect what we observe from far away. And so we can get away with kind of having crappy resolution at that singularity, but not on the event horizon itself.
That's really interesting. Thanks.
Just whilst we're on this question of AMR, can I ask why, in this case, the different levels of resolution are kind of rectangles? Well, why are they not kind of circles or sort of ovals around the black holes?
That's actually a really good question. So they could be, and actually we try different things. So it's really purely a kind of pragmatic thing. So in fact, actually, these aren't as rectangular as we sometimes use. This, you can see that they've got some kind of like jaggy edges. And often we would just use box within a box within a box within a box. So the reason for that is purely practical, that it makes it much easier to load balance if you know that each one is a cube, a kind of a rectangular cuboid. And also it affects the noise that you get. So if you want to, because we're using this adaptive mesh, it will dynamically refine and unrefine areas at the grid boundaries. And if you do a lot of that, it creates a lot of noise. So if you try to do a sphere, then your refinement will always kind of refine and unrefine at the kind of spherical boundary, just because it's trying to make a kind of Lego sphere of the sphere. And so we find that we get slightly more noise when we have sort of spherical regions, but not that much. So in some cases we have run with kind of, each one would be more of a kind of a sphere around each object. But it doesn't make that much difference to the speed and the accuracy if you just use rectangles.
I see. Okay, thank you. So I can see Simon's got his hand up.
Thank you. This is a much more naive version of, I think, a question that's already been asked. It sort of makes sense that you have to have very high resolution at the horizon, but the space-time curvature is getting larger and larger for smaller as the black hole gets smaller. So does that mean that it's actually harder to simulate small black holes than large ones?
Yeah, that is precisely true. Yes, that is precisely true. So in the case where I showed this one, so where you have this extreme mass ratio, the smaller one is much harder to simulate than the larger one. So the smaller one is where you have to really apply all of your resolution, and any kind of errors that you get there will kind of affect your gravitational wave signal. But yeah, absolutely, it's kind of, I always think it's counterintuitive. People always think smaller black holes are kind of less extreme, but it's not, as you say, it's not about really the size. It's about this kind of this curvature scale, and a shorter curvature scale is essentially more extreme in terms of strong gravity. So yeah, absolutely, these are the tricky ones.
Is there any possible selection bias if we can't do small ones as well as big ones? And we're seeing more big ones than we expect.
So I think in that case there is. So it's more about the mass ratio for the ones that we're seeing. Oh well, no. Okay, well there are two answers to this. So one answer is it's more about the mass ratio. So it's challenging when you have a very small one and a very big one. But there is definitely a bias towards solar mass type objects. So in terms of the frequency range that we're probing. So if we have very small black holes, the signals would be at much higher frequencies than the ones that LIGO observes. And there are actually no detectors in that range, so we wouldn't have seen them. So there's a kind of push to build gravitational wave detectors in that regime. There's not as much support for it because astrophysically you don't expect to find anything there, so it could just be a null result. a null result would be super interesting, I think. But of course, people don't want to put a lot of money into a null result.
It's super expensive null result. Yeah.
Exactly. Well, so there are some interesting proposals to use these kind of cold atom detectors. So I don't know a lot about it, but there are more kind of tabletop experiments where you could combine lots and lots of them together and gradually build up a picture at higher frequencies. So I think that will happen eventually. Eventually, people will go to higher frequencies, and as I say, it will be extremely interesting because anything we see there is completely, new, is unexpected. So I do hope that happens. Although I fear it would be a null result, and then I'd be disappointed.
Okay, I've got a couple of questions. I can see Andrea's got a question line as well. So you'll have to tell us once we're sort of imposing in hospitality and you want to.
Oh, that's okay. Don't worry. Yeah, I'm very free. Thank you.
Okay, Andrea.
Yeah. Hi. Thank you very much for the talk. I just have two very quick questions. So the first one, apology if you already explained this, but have you thought about using emulators for your simulation, and if not, why? And the other one is about when you talk about the curvature of time as an explanation of the expansion of the universe, if I understood that correctly. So under that perspective, like how can we think about dark energy in under that point of view, if it makes sense?
Okay, let me answer the question on emulators first. So people have been using emulators, and I'm afraid it's not something I know a lot about. But definitely people have been trying to use emulators for these gravitational wave signals. And then, these simulations that we do will be used to kind of, train the emulators and verify them in different regimes. The challenge that people generally find is that although these signals, it's kind of surprising, and perhaps, these signals to me, they all look kind of similar, and they look like you should be able to parameterize them relatively easily, and that you maybe should be able to smoothly interpolate between different parameters in a way that's quite straightforward. But it turns out that actually the differences that you get make quite a significant difference. So, if you go and naively interpolate between two mass ratios, maybe not so much, but things like spins, if you interpolate between spins, you can get very different behavior if you go and run the simulation at the midpoint compared to if you just kind of naively linearly interpolate the frequency or the amplitudes, for example, and the phase evolution over the signal. So it turns out to be, I think, a harder problem than you expect, to be able to interpolate in between these, the data points that you have from doing these simulations. But it's definitely something that's happening, and I think it's going to be I think people are going to kind of crack how to do it at some point. We already have enough that it kind of works. We have these sort of phenomenological models that are tuned. But I think that there's scope for it to be kind of cracked as a problem, and then, almost numerical relativity might be kind of put out of business, and, will just be used to kind of validate particular emulators, for example. But yeah, that's a growth thing. And then, okay, let me attempt to answer your question about the curve. So the curvature of time thing is really hard to see. So I guess maybe it's easiest to sort of show this picture. So the idea is that matter kind of curves the space-time. So in the context of dark energy, the dark energy is like the red ball in the sense that it's kind of existing in the space-time, and the way in which it exists causes the surface to curve in a particular way. And in particular, in the time direction, it causes it to kind of curve outwards in a way that trajectories on the surface tend to diverge. So yeah, almost like you could think of it like coming out of these lines. If you're traveling in a straight line here and a straight line here, you kind of naturally diverge away. And that's the way in which dark energy curves the kind of the space on large scales. I don't know if that kind of answers the question. It is really difficult to think about. I like to give this analogy because I think it gives you like a flavor and it gives you something to think about, but I don't I think it's almost like kind of grasping at something that's a little bit out of your reach sometimes.
No, I mean it helps, but it's such an interesting concept. Maybe it could be some sort of, because dark matter interacts only gravitationally, so maybe you can say, dark energy somehow, works space-time only, I don't know. I'm not like a theorist in that space, but yeah, thank you very much for your talk. It was so interesting.
Thank you.
So thankfully, Andrea asked 2 of my questions. Just firstly, though, if you want an emulator expert, you've already got one in-house. Juliana Kwan is definitely the person.
Okay. Oh, well, yeah, she's not doing that, or maybe she is doing it secretly. Maybe she's gonna,
That's basically what she was working on here, kind of emulations of cosmological simulations.
Right. Yeah, that's right. Yes, of course, she did cosmological simulations before. That's right.
Okay, so one quick one. So you say a simulation can take a week to run. So how many CPU hours are we talking? Is this a week to run on Dirac, on your laptop? I assume not your laptop. But...
Yeah, sadly not on my laptop. So yeah, I mean, roughly on sort of 500 to 1,000 cores. So one of the issues with these codes, which is what we're sort of hoping to get past with using GPUs, is they don't scale fantastically well to very high core counts. So we do, as I say, I think the best that we've sort of scaled to is sort of 4,000 cores, which is a lot, but it's not where we would like to be. And a lot of that is kind of inherent in how this kind of AMR structure works, and the time stepping that we have to do. But yeah, a typical simulation you can run on sort of 500 to 1,000 cores, and that's when it would take, of order a week or slightly less to do a standard binary black hole merger. So the ones that are very expensive are the neutron star ones, because you have so much additional physics. You have all of the hydrodynamics as well, and sometimes things like neutrino transport as well people are putting in. And so there are so many additional ingredients that actually the neutron stars are the ones that I think will benefit the most from going to GPUs, because there's a lot of complexity in the calculations that you can actually use the GPU for. But they can take about 6 months to do, just for one.
Wow. Okay, just one kind of final one then, before we let you go. So you touched on Star Trek, which means that I feel I'm able to go back to 3-body problem where we start.
Yes.
So have you tried simulating transferring a message through gravitational waves? How you would like sort of point, tell the universe where, like, an enemy.
Yeah, that's a really good question. You definitely could, right? So yeah, that's a really good point, because you can, I mean, you essentially, if you like rotate 2 bodies at some frequency, the gravitational wave signal that you get is 2 times that frequency. So you could totally vary the frequency at which they're going around each other, and therefore, frequency modulate the signal, the gravitational wave signal, in a way that would transmit the data. So I think it's when I say completely doable, I just mean in theory. But yeah, what you really need is 2 very dense objects where you can kind of move them around each other and control the frequency with which they rotate. And then you could frequency modulate that signal, and it would give off a gravitational wave signal that could carry data.
Yeah, it's really fascinating. I mean, this multi-messenger astronomy, gravitational waves. It's just we're getting this view of the universe in a completely different way.
Yeah.
I might be at the crest of seeing something completely. It change our whole view of what the universe is.
Yeah.
Like about those. I don't know how you don't have like existential dread every now and again doing that.
Oh no, I'm excited about the idea of seeing something new. That's why I like it. But yeah, maybe when it comes, it'll be something I don't like. Maybe it'll be aliens coming to it. If it's the warp signal, I don't know whether to take that as a good or bad sign. yeah, we'll have to see.
Oh, wonderful. Well, thanks so much for that talk. That was really, really fascinating. So yeah, we'll thank our speaker one last time. So next month we'll have Fabian Rohr giving a talk. He'll be talking about string theory and machine learning and all other interesting things like that. So yeah, hope to see you all there. And thanks again, Katy.
Thank you. Bye-bye.